In this video, we'll be discussing what Gaussian elimination is and how we can use it to put a system of equations into row echelon form. So as we mentioned in the last video, we really only have three operations that create equivalent systems, okay? And to remind you what an equivalent system is, it's one where the solutions are the same, and so it these operations sort of preserve, so to speak, our solutions to the system, okay? So these are worth knowing. So each of the following are what are called row operations on a system of linear equations. And each one of these three will produce an equivalent system of linear equations. The first row operation is we can interchange two equations. Another thing that we're allowed to do that creates an equivalent system is we can multiply one of the equations by a non-zero constant. Finally, the last row operation, which is one that we used a lot with solving by elimination, is adding a multiple of one equation to another equation in order to replace the latter equation. And again, the idea here is that we're trying to eliminate some sort of a variable in one of the equations. So let's see how we can use these row operations to solve the following system of linear equations. So first, starting with this system, I'm going to swap, and I write it as equation 1 and equation 2. So this was interchanging, right, or swapping the equations. This was the first row operation we're allowed to do, okay? Doing so, we end up with the system x minus y equals 0. And then we now have the top equation is the bottom equation, which is 2y equals 0. And when I say equation 1, I'm talking about this is 1 and this is 2. And throughout, I'll mean that. So now, this is equation 1, this is equation 2. Okay? So whichever one's on the top is the first equation, the one on the bottom is the second equation for 2. Okay? When we get 3, it'll be 1, 2, 3. If we had 4, it'd be 1, 2, 3, 4, so on and so forth. Okay? Now what we're going to do is we're going to multiply the first equation by 3 and add it by negative 3 and add it to the second equation. So I'm going to write add negative 3 times equation 1 to equation 2. And so I now have negative 3 through that. So what is that? That creates negative 3x plus 3y equals 0. And I'm adding that to 3x minus 2y equals 0. Those will cancel out. Here I get y equals 0. And sorry, I had a typo here. This is negative 1. So when I multiply by 3, that becomes positive. This should become negative 1 down there. Sorry. Nah. This is 0, and this is negative 1. This is 0, and this is negative 1. So y adding will be negative 1. That does illustrate a point, though. You want to be able to catch errors early when solving systems of equations, because otherwise you carry the errors through and it becomes harder and harder to find them. It's not a big deal when we only have 2 equations, but if we had 3 or even 4 equations, it becomes a lot harder and it just messes up all your computations. So we have y equals negative 1. We can back substitute now. So here, what have we really done? Well, what we've done is we've replaced the bottom equation with this equation. So replacing that equation, we're getting, we really have here, and I want to write it this way, x minus y equals 0, and y equals negative 1. Well, now this is in row echelon form, so I can solve it by back substituting. Namely, x equals, we have x minus negative 1 equals 0. That's x plus 1 equals 0, which means x equals negative 1. So we believe these should be our solutions, and so the solution should be -1, -1. Let's go ahead and check that one last time. In the future, I may not use time to check, but you should always check your solutions just to be sure. I mean, why not? I'm just trying to save time for you guys by not doing so. So let's check. We have 3 times -1 minus 2 times -1, which is -3 plus 2, which gives me -1, so that one works. And then for the second one, if I do -1 minus -1, well, since they're the same, we know that that's going to be 0. And so this isn't surprising, though, because, as I said, we always create an equivalent system of equations if we stick to those 3 row operations. So now it's time for you to try a problem. Go ahead and solve the following system of linear equations. On the count of 3, I will reveal the solution. 1, 2, 3. So here, when you actually solve that system out, you will see that, so first I swap, then I do an addition to get this equivalent, so I swap to get that equivalent system. Then I add -2 times equation 1 plus to equation 2 here to get a new equation 2. And this is how I'll typically write it in the future. Then, now that I have this, I know that I can multiply by -1/3, so I'll multiply equation 2 by -1/3 to get y equals 1. Now I have it in row echelon form, so I can back substitute to solve. And yes, in case you're wondering, I did check that both of these solutions work. It is worth noting that typically rewriting a system into row echelon form will usually require several different row operations, okay? Here I used one of each of the 3 I'm allowed to use, but in general, it can take many different ones, as we will see soon enough. So this process of solving a system by putting it into row echelon form actually has a name, which is Gaussian elimination. And this is named after the mathematician Carl Friedrich Gauss, who incidentally was actually probably the most prolific mathematician ever to exist. He's contributed to a number of different fields. We're now going to up the ante and try solving the following system of linear equations by doing row reduction on it. So first what I'm going to do is I'm going to eliminate this variable, the x in the second equation, by taking equation 1 and adding it to equation 2. Equation 1 plus equation 2 to get a new equation 2. When I do so, the top stays the same, x minus 2y plus 3z equals 9. The bottom, I always draw these too early. The next equation, I added the top equation to the bottom equation, so that becomes a 0x, so I won't write it. Here, I would get a single y. There is a typo. No, there's not. No, there's not. I'm correct. Okay. Here, adding, I get y. Yeah, I'd get a single y plus 3z. Right? Because the 3z will be there. And then I get 9 minus 4, which is positive 5. And then the last equation stays the same, right? 2x minus 5y plus 5z equals 17. So I have this equivalent system to the first system, all right? Now I want to eliminate the x there, so I'm going to take -2 times equation 1, add it to equation 2. This will, to equation 3, sorry. This will give me a new equation 3 here. And thus, what would I have while doing so? This stays the same. The second equation will stay the same, y plus 3z equals 5. But then the bottom equation, negative 2 times x will allow me to zero that out. Negative 2 times that will be 4y. Added to that will be negative y. Similarly, adding here, I would get negative 6z to 5z, so negative z equals negative 2 times 9 is going to be negative 18. Added to that will give me negative 1 there. So I have this system of equations now. And then if I continue, I'm going to eliminate the y here to be able to get this into row echelon form. And doing so, I will just add. So I'll take equation 2 and add it to equation 3 to get a new equation 3. And doing so, I have x minus 2y. The top equation is unchanged. Equation 2 is also unchanged. And then I'm going to adding these, I get a new equation 3, so I would get 0 there, I'd get 2z there, 0, so 0y, so why bother writing it, plus 2z equals 5 plus negative 1 is 4. And then finally, as my final step, I'm going to multiply by 1/2, so multiply equation 3 by 1/2. In doing so, I end up with the system x minus 2y plus 3z equals 9, y plus 3z equals 5, and z equals 2. And now now that I have it in row echelon form, I can back substitute, and back substituting will actually end up giving me 1, negative 1, and 2. And if you watched the last video, it's because this system is exactly the system that we solved out that we used back substitution to solve out in that video. And now it's time for you to get in on the fun. So go ahead and try solving the following system of linear equations using Gaussian elimination. On the count of 3, I will reveal the solution. 1, 2, 3. So here we do a series of row operations. This is the most third one is the most complicated one we've seen so far. We have to multiply this to eliminate the y in the equation 3 here. We have to multiply by negative 2 this equation, and then so the middle equation we multiply by negative 2, and we add it to 3 times the bottom equation, equation 3. That's what we're doing there. And by that we get negative 10z equals negative 30. As such, I went ahead and wrote out all my steps, including the check. But when you go through it, you will see that indeed 1, 2, 3, I know, I thought it was funny too, that 1, 2, 3 is in fact the answer. For more practice, be sure to see the textbook, pages 498 and 499, and work those problems mentioned there. In our next video, we're going to investigate the number of solutions of a linear system.